So guys, now let us start with understanding of the algorithm to construct IPv4 routing table. So to start with, we have a root node of the mtry, and the root node initially is empty. It do not have any effective prefix. The prefix len is 0 and all the pointers of its children are null. Here 1 represents the node ID. So I have taken a node ID only for the sake of making our discussion a little bit easier so that I can talk about this node and that node with the help of node ID. Otherwise, node ID has nothing to do with the algorithm. It is only for the sake to identify that which node I am talking about. So to start with, let us say that we need to insert a route 1.2.3.4/32. Alright. So the very first thing that we need to do is to convert this route into its effective prefix form. So this is the effective prefix for this route. Alright. And when we say route, it also means that you are also saying that when this route is used for forwarding the traffic, then which is the next hop to be used? So next hop is some data structure which is in memory somewhere else. Alright. And we call the data of this route as that next hop, that is the address of that next hop. So every route is associated with the next hop, and the data part is nothing but it is the next hop object which is associated with that route. Alright. So the next thing that we need to do is to insert this route into our mtry data structure. So insertion of the route always begins from the root. Now in order to insert a route, we will going to examine the very first bit of the effective prefix bit of a route. In our case, the very first bit is 0. Alright. So it means that we need to insert this route as a 0th child of the root node. And it's over. Alright. So the new node that is just inserted has been given a node ID, say 2. And because the effective prefix of this route started with bit 0, so we will going to insert this particular route as a 0th child of the root node. So for the node 2, this is the effective prefix, this is the prefix len, and this is the data part. And obviously all the children of the node 2 will point to null. And now the 0th child of the root node points to the node 2. Alright, so with this, the insertion of this route is successful. Similarly, if you want to insert the route 128.234, quickly convert this route into its effective prefix form. So this is the representation of this route. And examine the first bit of this route, which is 1. So again, the insertion of the route begins with the root node. So we will going to create a new node with node ID say 3, and we will make this new node as the 1th child of the root node. And the node number 3 will going to contain the effective prefix as the following, and this is the prefix len, and this is the data part. Alright, so we have successfully inserted the route number 2 in this mtry data structure. So things are pretty much easy and simple. We just scan the first bit of the effective prefix of the new route, and based on that we insert a new child node as a child of the root node. Similarly, suppose you want to insert the route number 3, which is a default route 0.0.0.0/0. So the effective prefix representation of this route is nothing but all don't cares. Alright, so the first bit of this effective prefix is don't care. So it simply means that you need to insert a new child node as a don't care child of the root node. Alright, so for the node number 4, the effective prefix is the following, and the prefix len would be 32, of course, I missed it, and the data part will point to the next hop of this route. So far the things are pretty much easy and simple. Now let us talk about insertion of the route 128.2.0.0/16. Alright, so now things becomes a little bit non-trivial. So let us convert the route number 4 into its effective prefix form. So you can see this is the route number 4, which is converted into its effective prefix form. Now let us start traversing the tree starting from the root node. So the first bit of this new route is 1, so we will traverse the child number 1 of the parent node. So we reach the node number 3, and once we descend down the tree, we do the prefix matching. So we will going to match the effective prefix of the node 3 with the effective prefix of the new route, and we find that the first 16 bits of the node 3 matches exactly with the first 16 bits of this new route of the effective prefix, of course. So it means that the bit which is highlighted in pink color is the bit at which the mismatch happens. So whenever in the route insertion a mismatch happens, like this case, the node present in the M-trie at which the mismatch happens will undergo node split. So it means that node number 3 will undergo node split procedure. Now what is node split procedure? Let us discuss that. So guys, now let us discuss how node split procedure is executed. The node number 3 will undergo node split because while traversing down the M-trie from the root node, at node number 3 there occurs a mismatch in the effective prefix of the node 3 and the effective prefix of the new route. The bit at which the mismatch happens is shown in the pink color. Alright? So this is the point at which a node number 3 will undergo node split. So as a part of node split procedure, the very first thing that we do is that we will going to create 2 new nodes. The node number 5 and the node number 6. The node number 5 is called a daughter node, whereas node number 6 is called a niece node. Now node number 5 is called a daughter node because as a daughter of its parent, the daughter node will borrow the possessions of its parent node. Now what are those possessions? First of all, the daughter node will borrow the bits from the effective prefix of its parent node. From the point where the mismatch has happened up to the last, all the bits from the effective prefix of the parent node is copied as it is as the daughter node effective prefix. So actually it is not a copy, but it is a transfer. So as we are transferring here 16 bits from the parent's node effective prefix to the daughter node effective prefix, therefore parent node effective prefix would be shrinked by 16 bits. So the new prefix length of the parent node would become 16 because the latter part of the 16 bits has been transferred to the parent node. Alright, so the parent node's prefix length would become 16. This is the first thing. Now why we have made the daughter node as the 0th child of the parent node? Because the bit at which the split happens is the 0th bit. Alright, so it means that the daughter node will become the 0th node of the parent node. Then daughter node also borrows the data of the parent node. So whatever be the data pointer of the parent node was, the daughter node will borrow that data. Alright, so the data pointer of the parent node would become null. And the third thing that the daughter node borrows from the parent node is the children of the parent node. So in this case, we did not have any children of the node number 3 before the node number 3 undergo a split. But if it had any children, all those children will be transferred to the daughter node. So we will see this procedure when we will going to split the node which already had children in our subsequent example. So this was the story of the daughter node. The daughter node borrows 3 things from the parent node. The first is the bits from the effective prefix of the parent node. The second is the data of the parent node. And the third is the children of the parent node. Alright, and obviously the prefix length of the parent node would get reduced after a split depending on how many bits have been transferred to the daughter node. Then the second node is the niece node, which is very simple case. the niece node will borrow its effective prefix bits from the effective prefix bits of the new route, right? So from the point where the mismatch has happened, we will going to copy the prefix bits of the new route as the prefix bits of the niece node. And here, since we are copying the 16 bits, therefore the prefix length of the niece node is 16. And obviously the data part of the new route will be copied as it is as the data part of this niece node. And obviously, since the niece node is a new node, all of its children points to null. And why this niece node is made as a don't care children of its parent? Because the first bit of this niece node is a don't care. So this is the procedure of splitting a node. You can rewind this video and go through the explanation again to understand it better. However, we will going to insert few more routes in this tree, and we will going to discuss node split algorithm few more times again. So the following points needs to be highlighted. Data of the parent node is transferred to the daughter node. Transfer of the effective prefix bits of the parent node to the daughter node, and transfer all the children of the parent node to the daughter node. Alright, so you can see that the daughter node is notorious in the sense that it takes away all the positions of its parent node which is undergoing a split. Remember that. So the next slide shows that how does the M-trie data structure looks after the insertion of the route 128.200/16. This is the pictorial representation of the M-trie data structure before the insertion of the route, and this is the pictorial representation of the M-trie data structure after the insertion of the route. And you can see all the changes has happened in the node 3 and downwards. The node 2 and 4 of this M-trie data structure is untouched. You can see the data part of the node 3 is null. The prefix length of the node 3 has been reduced from 32 to 16. The bits from the effective prefix of the node 3 has been transferred to its daughter node. And the niece node borrows its effective prefix bits from the bits of the route which is just inserted. So now, can you write the steps regarding how the node split algorithm can be written in simple plain English words? Can you do that? Let us do that in the next lecture video.